Can you see my slides?
Yes, we can see it right now.
Perfect. Let's start. Thank you again for the invitation. I'm Ali Najafi, and I'm currently a senior master student at Sabancı University in the field of computer science. And I'm right now one of the members of our lab. And basically, the field that I worked on it is NLP. And in the past year, in the lab, we built Turkish Bear Tweet language model solely on Twitter data. And yeah, let's start with the model architecture that we used for building the model. So we used basically the BERT-based language model structure, which is basically the encoder side of the transformers model, which came out 2017. The size of our model is around 163 million. And well, basically, compared to BERT language model, which is one of the well-known ones, it has less parameters, around 21 million parameters, which makes it super fast in terms of inference. And I will show you the stats in future. Also, the input length of this model that we trained was 128. So it means we basically in one pass we can feed the model 128 tokens, and we set the vocabulary size 100,000. This vocabulary size is quite big compared to the other models, and the reason we selected a big vocabulary size was because of the nature of Twitter, as people are using quite weird characters sometimes, and or they may generate new tokens, new words in the time, which may be, let's say, for example, no one was, let's say there was no word COVID, let's say, but nowadays after some pandemic, people are using that a lot in different contexts. So now that word is a new word in the Twitter, or let's say RT, which stands for retweet. In the past, let's say 50 years ago, there was no word as RT, and nowadays we are using it as a retweet. So this huge vocabulary size is to help the model to capture those new and weird vocabularies. So we trained our model on a big training data. Basically, we had this data set of 10 years solely Twitter Turkish data. In the volume size, it is around 110 gigabyte unpressed text data. It was around 190 million tokens. And so we trained our model on this data. We applied some pre-processing and filtering, like removing the duplicates to kind of avoid over descending. And also one of the criteria of our filtering was choosing the tweets having more than 10 tokens. More than that, we had another extra pre-processing step in our pipeline, which was basically dealing with the entities we have in Twitter. For instance, we have mentions, hashtags, cash tags, emojis, URLs, and emails. All of these things are present in Twitter, and you have seen them. So we first of all replaced the mentions with @user general token to kind of avoid the privacy issues. Secondly, we added these boundary tags to kind of help model, saying that model, when you see, let's say, open hashtag and close hashtag, we expect you to not let's not say generation, but generating, or let's say unmasking a token which is hashtag like or hashtag like. For emojis, we translated the emoji thingy with the equivalent text of it in Turkish. URLs replaced with domain, though this was not that helpful, because in Twitter usually the URLs .com, all of the domains basically gets converted or shortened to something like t.co. So it's didn't help us that much. Also, we replaced the emails with the email tag. So these are some analysis, like statistical analysis on our pre-training data to see everything looks fine. So the left side, you see the token level distribution. At the right side, you see the character level distribution. And there are lots of characters, lots of tweets with the character size of 140. And the reason for that peak at the right side you see there is it was basically the limit of Twitter not letting the users to tweet more than that amount of characters in one tweet. But since this data is on the span of 10 years, so it's quite reasonable. This is the special tokens distributions. And at the top left, you see the users distribution, mentions distributions, HTTP distribution, and so on. Majority of, for instance, tweets, around 10 to the power of 9 number of tweets didn't have, for instance, user mentions, and so on. These are just some analysis for the special tokens. We trained our model on V3.8 TPUs of Google, and thanks to Google, we got these TPUs for free, which was super helpful. We trained our BERT-based model on Roberta's masked language model and objective. The reason we chose this, in the BERT's paper, as it is mentioned, it was trained on 2 tasks: masked language modeling and the next sentence prediction. So, and in the Roberta's paper, they showed that masked language modeling is quite enough to learn basically the language. Our basically batch size was 1024 in total, and we trained the model for 8 days. And our learning rate was, first of all, we started warming up, and then after that, we reduced the learning rate linearly. And as you see, the train loss, we reduced down up to around 1 to 1.3. And this train loss is basically nothing but, if I'm not mistaken, it's like cross entropy loss. So once we train, the training objective was definitely masked language modeling, and right now the model is open source on Hugging Face. You can easily access and download it. Like for instance, this is one of the examples. As you see, it is in Turkish, and you see the distribution of, order distribution of the words that they can be replaced in the mask. By the way, if you, for instance, put, let's say, emoji open tag, then mask, then close emoji tag, that mask will be get predicted as something similar like emoji text. So once we trained our model, it's time to evaluate our model on some tasks. So we trained, after training, since we trained on solely Twitter data, it was quite important to choose the data sets that they align with our pre-trained data. Since our data was Twitter data, so we had to find the data sets that has basically the nature of tweet tweets basically, and there should be short and wild, informal, and so on. And so we have these data sets, and some of them you see there basically the distribution of the data sets. So the first task was sentiment classification.
Mr. Ali,
And
sorry
yep.
for interrupting, but I think there is a problem with screen sharing right now. We can see that you are sliding.
Okay, are you stuck in the first slide?
Yeah. Okay, it fixed it right now.
Can you see right now?
Yeah, we can see.
So from where you couldn't, we couldn't continue. What was the last slide you were seeing, basically? I just want to ask that.
I think first one, yeah.
First one? The beginning? Oh, you should have informed me earlier. We passed a lot. So, okay, let me recap everything. So we had this model architecture, and then we had this pre-trained data. And after that, we did some pre-processing, like entity pre-processing steps. After that, we had the distributions of our pre-training data, and then also for special tokens. But I think you don't see the full slides. Give me a sec. Do you have right now the slides?
We are in spatial tokens distribution.
Okay. Do you see right now the next slide?
No, we are still in the spatial tokens.
Okay, I don't know why there is this issue. Let me see. Because let me present my full screen. Okay. Okay, how about now?
Yeah, we can see.
So how about now?
Yeah.
Okay, perfect. Now you see the training reports. Okay. Yes. So as I said, we had this special tokens distributions, and after that, this was the training reports. We trained the model until the train loss came to something like 1.3, and we trained it for 8 days. And this was the an example of unmasking that you can use our model for. So after pre-training our model, it was the time to evaluate it, and we chose two text classification tasks. And if you may want to ask why not other tasks like name entity recognition and so on, because those data were not available for us. Unfortunately, the Turkish NLP community didn't have enough resources in that regard. So we basically played with the cards we had in our hands. So for sentiment classification task, these are the dataset names: Varolab Varol sentiment and TSET tweets. Thanks to Chemic team, they provided us those datasets, and also Boğaziçi University's dataset that we used. Also, we had this hate speech dataset from the computational social science competition that was basically held previous year by Sabancı University. And it was the hate speech classification task. So based on these two tasks, we had, it was the time to fine tune our language model on these tasks and see how it works compared to the other models. So for fine tuning, there are different ways. The traditional way was basically updating the weights of the main model, the pre-trained model on the task, which was okay. And recently, LoRa fine-tuning came out, which is a quite efficient way of fine-tuning. I will show in the next slides how it works. And also quantized LoRa fine-tuning. So LoRa fine-tuning is nothing but basically keeping the pre-trained weights of the model, let's say we have Turkish bird tweet, we don't update any of these weights of the model. You can see it as a as this blue box at the left side, and then we inject these LoRa adapters for each layer, and these adapters are like basically in the architecture of autoencoders. And there is this bottleneck. They call this bottleneck or rank, or as they define it as R. And what they learn in this, while doing this, is nothing but basically gradients. So at the top right, you see this, very famous formula of gradient descent, right? We have, previous weights, and we learn, we calculate the gradient descent, and then update our weights. So this was the normal way of fine-tuning previously. But now with LoRa, we say that let's keep the pre-trained weights. So this WPT you see here is static. We don't touch it at all. And we ask the model to learn instead of calculate it. So basically gradient descent itself calculates this gradient descent, okay? This gradient. And in the inference time, let's say we have this X as input, we give it to the blue box, okay? Basically our model will give something out. And also we pass this X to this injected layer, and then we just add these two outputs, and the final output is basically the updated version of the model. It is quite efficient. Why? Because in the normal fine-tuning, let's say your model size is 7 billion. You have a model with the 7 billion parameters. And if you want to fine-tune that, you have a very hard task. You need to update all of the weights, and you should have a lot of data as well. But in the LoRa fine-tuning, let's say you don't touch any parameters of 7 billion model, and you just, let's say, update LoRa adapters, which has, let's say, 20 million parameters. It is quite, useful, and also the output, the performance is super good. And normally this bottleneck is 8, 16, 32. It's on the power of 2 to the power of n. But normally they set R as 8 or 16. As much you increase this R, actually the performance of the model becomes like the performance of the pre-trained model. So there is no basically any improvement. So just a quick summary about the quantization. Quantization, this is the simplest way that I can define, but there's a heavy research going on in the field. So let's say we have a network, as you can see, and so each of these weights are a float number, normally float 32, and float 32 is 4 byte, right? And imagine you have 7 billion, a model with 7 billion parameters. So 7 billion multiplied by 4, it's amount of the memory size that you need to load the model. But if you quantize it, what we mean with quantization is we basically convert these weights to some numbers like this, 6, 8, 13, 4. It's not like just grabbing the whole, the integer size of it. It's nothing, it's not that simple, okay? But with doing that, with this way, now instead of like 4 byte, you are using int 8, and the model size gets reduced down by 4. Okay, simple. And the performance of the model is something similar to the main model. Definitely, sometimes there is this downgrade in the performance, but all in all, it is really good. Also, sometimes we may see a positive performance as well. You see that the quantized model is better than the main model. Sometimes it is good because it's kind of a regularization. Like maybe the model learned too much complex patterns, and once we are doing this quantization, model gets simpler, and it's like things simpler and it performs better. So there is also this side of the quantization. So we did a comprehensive analysis. Like we did LoRa fine-tuning, normal fine-tuning, and also zero-shot prediction. We compared our model's performance with BERT-TURK, MT5 Large, Llama 2, and multilingual BERT, and Ludus Albert. And our main competitive was BERT-TURK. And as you see, our model's performance is sometimes better, sometimes worse, but not too much compared to BERT-TURK. But as you see, with LoRa fine-tuning, the performance of the model gets increased by 7-8%, which is quite a lot. And also on the hate-speech task, you see that here on our own analysis, you'll see Turkish BERT is just a little bit, 1% worse than BERT-TURK, but in future you'll see that our model outperformed BERT-TURK again. And need to mention that instead of, by the way, just reporting one single, let's say, number as a final performance of the models, we did k-fold cross-validation, 5-fold cross-validation, which took a lot of time, by the way, but to make sure that all of the results are consistent. In this table, just want to mention that you see BERT-TURK is performing like really good compared to other models on Boğaziçi University's data. What we are suspicious about is the data leakage in the evaluation. And BERT-TURK can, I think BERT-TURK has seen some part of the data in the Boğaziçi University, and you will see in the next analysis. So moreover, aside those single dataset analysis, we did out-of-distribution analysis as well. Like, let's say we have 5 datasets. We trained our model on 4 of them, and then we evaluated on the held out one. You see our model is performing super good compared to BERT-TURK. And except in Boon, again, you see this high performance in BERT-TURK, because I think BERT-TURK had some data from in that setting. We also get the performance of ChatGPT 3.5 Turbo, and just 2% or 3% better performance, and sometimes not better performance compared to the other models. It shows that you can use these simple small models, which they are free, by the way, and get almost the same performance, and you wouldn't pay any penny for that. In terms of inference and the speed, we did this benchmarking. So on a single GPU of GeForce RTX 4090, which had 24 GB VRAM, as you see in this column, we have the size of the models. Turkish Albert base is super small, so of course, its inference time will be, the best. But if you just look at it, our Turkish BERT is 163 million parameters, and there's just 0.1 seconds difference. And we did this on 1,000 samples. And with the batch size differs because we wanted to have the best performance for each model. And you see in the best setting, our model is faster compared to the other models. In terms of applications of the model, we have our datasets in our lab, Seçim 2023, which is basically contains the data for elections, for the previous election in Turkey. On this span of a year, let's say you wanted to see the trends of the sentiments in Turkish Twitter. And as you can see, it's quite I mean, it aligns with the events that happens in Turkey. So you see the New Year here, you see the unfortunate earthquake in Turkey, and also with this analysis. So this is one of the applications of our model. In terms of cost, so the time we were like doing the cost estimation on ChatGPT, it was quite, expensive. For instance, if you want to do a huge analysis, let's say if you have a lot of data and you want to use ChatGPT, it was quite expensive those days. But after some time, they reduced down this cost. But even with the current price of ChatGPT, if you want to just infer, like on our data set, which we calculated, like on our data set with their OpenAI's token counter, we had 40 billion tokens. And if you want to just infer, no fine tuning at all, you need to pay $41,000, which is quite a lot in terms of research. So that is one of the caveats of the ChatGPT or OpenAI, products, or similar other products as well. One of the problems with those models is those models are not public, and so in order to use them, you need to give your data. You need to upload your data, or you need to basically provide the data and get the output. If you are dealing with sensitive data, let's say if you are using the medical data, which basically in order to access those data, you need to sign a lot of contracts. It means no. It's like big no. You are not going to use those company-based products. You need to have your own system. So that's also one of the beauty of the open source products. So we also, basically participated in EACL workshop, this year's EACL 2024's workshop, and using Turkish Bird Tweet, we basically ended up in the top third rank in the competition. And this EACL is also going to be held, I guess, in 10 days in Malta, and we are going to also participate there and present our work. Let me show what we did. So here, we basically fine-tuned Turkish Bird Tweet again with LoRa, and also BERT LoRa. And we did also ensembles of models. So the task was basically hate speech detection. And in our internal evaluations, you see that ensembles of models was super good compared to the rest, but we gained the highest public score for Turkish Bird Tweet. And what is the difference between public score and private score is in these competitions. So let's say we have evaluation data set. This public scores only shows the performance of the models on 20% of those data. And the private scores are not shown there. And once everyone, competition is done, they announce the private scores. So we chose Turkish Bird Tweet as our main submission, and we gained the highest private score compared to other models, which again shows the efficiency of our model in these classification tasks. We did also extra misclassification analysis. Like as you see in the table, Katil Israel, hashtag Katil Israel, which means the murder Israel was annotated as not hate speech. Why these things exist in the data set can be because of the definition of hate speech. If you're an annotator from Middle East, you may not find Katil Israel as hate speech, but also you may support that. But let's say you're a Western person, and while you're annotating, you may say that, no, this is hate speech, okay? And so that's also one of the caveats of or let's say gray areas of these tasks. So finally, I would like to introduce our lab members. So as you can see, Dr. Onur Varol is our PI at Varol Lab, and also the rest of the team are there. We have open positions for grad students, and recently we won many grants from European organizations like Chistera, also Horizon, and also we have the current TÜBİTAK projects going on. So if you are interested in computational social science and or basically or interdisciplinary fields, it can be political science, it can be international relations, or basically any other field than computer science. We are welcome. So you can check varollab.com website to see the open positions. And if you found it interesting, you can definitely apply. And that's all. Thanks a lot. And if there's any question, I would be glad to answer.
Is there anyone who has questions?
Okay, perfect. Thank you again for inviting, and I hope that it was useful for the people who were here, and have a great night.
Thanks for all your contribution to this event, Mr. Ali.
No problem at all. Bye-bye.
Bye-bye.
Thanks, Ali.